Thank you very much, Dario. Thank you, of course, for the invitation. It's too bad I couldn't come for longer, but the teaching already started, so I cannot really escape for a week or two. I actually want also thank organizers. This is my favorite format. So when we have few amounts of talks and a lot of time to discuss, maybe to think, I really like it. And it's less intense, but at least I personally learn much more from this kind of workshops. So I will talk about chaos and thermalization, and this is the topic I and my collaborators, some of whom I hear, were studying for already quite a few years. So, but each time, and there is overlap with some recent conferences, so each time I prepare this talk, I try to update at least half of the slides, just to focus on different things, and that's what I did for this talk. But there will be some overlap with what I was doing for a while, because there are also new people in this room. So I will maybe start, and this is the part precisely which I'm emphasizing in pretty much any talk devoted on chaos, in just general idea how we think about chaos. And then I will maybe talk to scenarios. And I very much welcome questions during the talk. Maybe I won't finish everything, but I think it's more lively. So we know traditionally chaos is defined through instability of trajectories in classical systems, and quantum mechanically it usually defined through various violations of random matrix theory, or not violations, sorry, manifestations of random matrix theory, which could be level statistics, form factor, and so on. But let me say just from the beginning that these two definitions, sometimes they have overlap, but sometimes they're really incompatible with each other. And the simple example, I ran into this when I was teaching graduate quantum mechanics. I thought I use this nonlinear, two-dimensional nonlinear oscillator, which is clearly chaotic, as you see from the picture, to illustrate random matrix statistics. And then I broke all the symmetries, and then I realized it doesn't work. So you can never get anything but tiny deviation from Poisson statistics. Then, of course, I realized that people knew it for a long time. So this is not a billiard, and in not a billiard, random matrix theory just simply doesn't work. But the system is clearly chaotic. So on the other hand, it was also realized quite recently that Lyapunov exponents, or out-of-time autocorrelation functions, they actually don't work in quantum systems. Again, systems which are close to classical limit, I'll come back to that, some special models like SYK, it works, but generally it doesn't. So, and then also people thought about more recently short-time expansions, Krylov complexity, and so on. This also doesn't work for classical systems. So this definition is not compatible with chaos. But now we can take a step back from mathematics and look into pictures. That's how, at the end, we think about physics. At least I think about this as trying to reconcile mathematical formalism with what we see, right? And then we see usually we associate chaos with some turbulent flows or with pictures like this. And you can immediately see that chaos is not about thermalization. It's not about random matrix theory, right? This system is highly non-thermal, even at any scale. And it's also chaos is not about, you see, it's about not about thermalization. You can see from these pictures. Tau-less time is roughly when picture becomes like this, blue. But chaos appears long before that. So we have to distinguish this concept. See. Okay, so, and then actually unrelated to these pictures, it was sort of like random rendering in theory space. We thought by we, I mean Mohit Pandey, who was the student at that time, and also Dries, who is here, was heavily involved, and Peter Kleiss and David Campbell. We thought about, okay, maybe in quantum systems we can think about chaos as instability of eigenstates in analogy with instability of trajectories. And the measure of instability is well known. It's fidelity susceptibility, Fubini study metric, quantum Fisher information. It appears under different names. But it's basically overlaps of derivatives of eigenstates. It just tells you how quickly your eigenstate changes if you add tiny perturbation, right? And this instability, this actually works. And here I show an example from an unpublished paper led by Patricia Lidze and also in collaboration with Lev Vidmar. I'll come back to this. It's an Anderson insulator. It's an example very close to the heart of this workshop. And here we study this fidelity susceptibility, or it's actually not V is a strong statement. I'm not involved in any of numerics, but it's mostly Patricia who is and her student who are doing numerics. So this is fidelity susceptibility for different observables. You see different set of lines as a function of disorder. And I only want to focus here because at weak disorder, the system is also integrable. If you want, ask me later about this, why there is a difference and so on. But let's just focus on this. And then you see there are 3 different observables plotted. And all of them, as you increase system size, you go from yellow to blue. They show like peak exactly at the transition. And that's where we roughly see the system most chaotic. It's also slowest, as I'll come back, like fidelity susceptibility tells us about how slow dynamics is. But it's also most random. So it's probably this one of these fractal phases. So again, if you talk to a person outside of the street, they will point that this is very chaotic. And the idea actually to use fidelity susceptibility as a measure of phase transition came from Venuti and Zanardi quite some time ago in 2000s, almost 20 years ago. And they thought about this as kind of observable free measure to detect quantum phase transition, detect criticality. And I'll talk.
Sorry, can I ask?
Yeah.
So here, how I remember when I worked a bit on this, I never know how many eigenstates do you need to compute and to have something stable about that? Because in principle, you can compute for one eigenstate.
Yes.
But I had the memory that the measure was a bit, let's say, noisy by changing eigenstates.
Yes. There are light fluctuations.
So I remember that I was not super sure about what to do, let's say.
Yeah, this is average of eigenstates. It's a typical susceptibility. But you're right. Once you're close to localization transition, you know that you have huge fluctuations.
And so,
but the same happens, by the way, I'll come back to this classical systems. When you have mixed phase space, it's like some trajectories are localized, some delocalized. You have huge fluctuations.
So in particular, let's say, probably I can ask this more to Leo. This plot is not obtained by full diagonalization, right? You were diagonalizing in a small window and taking.
This is full diagonalization, but limited. Just analysis is done in a narrow window around the middle of the spectrum. But this is single particle state.
Okay, sorry. This is single particle.
You're right. Okay.
Well, actually, with Dries, we were involved in these disordered systems, interacting systems. And there, actually, Dries did a lot of numeric studying distribution of this fidelity susceptibility. It was done, actually, also by Kuba Zakrzewski. Actually, when I speak Russian, I can pronounce his last name like this. But when I speak English, I always bump it. So it's funny. Anyway, so they looked into random matrix theory. There is a lot of, let me say it like this. Fidelity susceptibility is just a number. Physics is more than a number. So you can study like moments of these fluctuations between eigenstates. Whenever you go to chaos, everything becomes like chaotic, fluctuating, and so on. Okay, but anyway, so this is just to show it works, but now let's try to connect it to physics, because sometimes people say like eigenstates about random matrix statistics. Quantum chaos is about random matrix statistics. This I personally don't like to accept, because eigenstates is a language. It's a language we use in quantum mechanics. It turns out we can use it in classical mechanics. It's not very well known, but it's a simple statement. Maybe more of you know that I can use phase space in classical mechanics. I can also use it in quantum mechanics, a Wigner-Ryle function. Reverse is also true. So it's a language. It's a very convenient language for quantum mechanics. But when we talk about phenomena, we need to talk about physics, about observables. So let's try to connect this fidelity susceptibility to observables. And there is like probably one or two, I have technical slides. So if we think about what is the overlap between eigenstates. So well, it's a matrix, right? And this matrix we will call H. It's a diabatic gauge potential. And overlaps we can understand from perturbation theory. At this point, like degeneracies don't really play a role here, so I'll regularize it anyway. So it's basically we know overlap of for eigenstate derivative, overlap of derivative on the eigenstate with another eigenstate is a ratio of the matrix element over energy denominator. And then it's very easy to see if I use, say, Lemon representation, I can relate it to a time integral of a Heisenberg operator, right? So there is alternative representation, which is sort of more intuitive. So the reason I have to introduce this sign, I want to have principal value, right? I want to exclude delta function. But there is another way to exclude delta function, just subtract time average. And then instead of introducing this weird sign t, I can integrate from 0 to t. T plays the role of 1 over mu, and this is like a frequency cutoff. And I just integrate, essentially I integrate my time-dependent operator from 0 to time t. And then in principle, I should take the limit mu goes to 0, but very often, as we know, physics is how we approach limit mu equals to 0. Limit itself, by the way, might not be even well defined. Okay. So, and you can actually think about A is momentum, which is conjugate to coordinate, and it's actually correct if you think about dynamics of your, say, external parameters of the degrees of freedom, but this is a little bit outside of the scope of this talk. So, but this adiabatic gauge potential is also defined in classical systems, and it has a meaning of a generator of canonical trajectory preserving canonical transformations. So if I deform Hamiltonian slightly, how I need to change coordinates to get same trajectories. So it has well-defined classical limit. And then finally, if we use this representation, then it's very easy to see that fidelity susceptibility, which is basically size or norm of this operator, is essentially integral of spectral function, noise, dissipation, if you wanted, what enters Fermi-Golden rule rate, divided by frequency squared and integrated over frequency starting from the cutoff. So it's a low frequency noise. And this is actually the key to what I'm going to describe next. We see that low frequency signal indicates chaos. And now let's see how it works pictorially. And here I will show classical pictures because we have more intuition. So it's the same two-dimensional nonlinear potential I showed in the beginning. But here we just look into one particular observable, say it's adiabatic invariant or energy of first oscillator as a function of time. Of course, it's not conserved because I have two oscillators which are coupled. And then this is, again, a classical picture. The two pictures show that what happens if I have one Hamiltonian with, say, two identical frequencies and another Hamiltonian with slightly different frequencies. So it's slightly different Hamiltonian, the same initial condition. And this is a small nonlinearity, and it's a particular trajectory, no averaging involved. It's, if you want, like one eigenstate. And then you see visually there's no chaos. And you see it from the fact that it's a very nice picture, and you see it from the fact that if I change something, nothing really changes. So, you know, there should be very simple map from left to right picture. Now we take exact same model and increase nonlinearity a little bit. And now, again, you see immediately, yes, there is a chaos. And you see it in both ways. So first, you see that it's very irregular motion. And second, you see it's very unstable motion. You change Hamiltonian a little bit, you get totally different trajectories. And this is, I would say, this is how we understand chaos if we forget about physics. Like you can go to, hopefully not you, but if someone, say, goes to a doctor to measure your heartbeats, they recognize chaos without need of having like another copy of you with slightly different conditions, right? They measure irregularity. So same if you see it in the airplane and turbulence starts, you know you have a chaos. You don't need a second airplane. You see irregularity. But we also think about chaos as butterfly effect, right? Which tells us about instability. You change something in your Hamiltonian and you get something totally different. And then what I want to argue that interesting, these adiabatic transformations or spectral functions, they actually know about both. So And I'll tell you why, because first they tell about instability of eigenstates or trajectories, but they're also relevant to low frequency noise. And when you see chaos with your eye, you actually realize low frequency noise. It's very interesting. Okay, so now let's just again see how it works. What are the different regimes of chaos broadly? So I come back to this representation that this adiabatic gauge potential is just integral from 0 to t of your observable v of t. And actually, the role of observables could be also important closed integrability breaking. And then we can have basically three scenarios. Integrable systems, again, I appeal to classical systems because you have more intuition. We know that our observables are kind of combination of periodic orbits. Again, let me not worry about thermodynamic limit here. So we think about some finite systems. So you have some finite frequencies, and then if you integrate your observables at time, it's constant. It doesn't depend on upper period. And then chi, which is just square of this, is also constant, right? Another example, when we have ergodic systems or mixing systems, then we know that our correlation function between v of t1 and v of t2 decays quickly, usually exponentially, but could be something else. So this integral then diverges as first power of time, because integral over relative time is a constant, right? But then there is another third regime, critical subdiffusive thickly mixing. I'll probably mention a bit more about this. It's when correlation functions decay slowly, and slowly means slower than 1 over time. In this case, this integral is even more divergent. And it's most divergent when they start decaying logarithmically. It's in time. It's a critical scaling. And then the maximum we can get is t squared. So we see that from this analysis that systems with slow dynamics are actually more chaotic. They have more unstable trajectories. And that's actually what butterfly effect is about. I'll come back. It's not about Lyapunov exponent. And this is an example. This is not even Hamiltonian system. It's Monte Carlo simulations of phase transitions. And you visually recognize close to the critical point when we have slow dynamics. It's extremely chaotic. So these things really come together. Good. So now I go to my talk, and I will start talking about three different scenarios, and maybe there are more, of how chaos and thermalization emerge. And I will use specific models, and then I will speculate that these are generic scenarios, but again, no, well, in some cases there are proofs by other people, in some cases there are no proofs. So we focus on classical models, though I show some examples of quantum, because they are easier to study. You can study like big systems, you don't have finite size effects and so on. And one example I start is called Ishimori chain. It's analog of quantum Heisenberg's chain. It has some weird log interactions, and S is a continuous vector. So think about this quantum model when spin is infinite. And then it's known that this model is integrable. And then we perturb it with small disorder. So then there are many conservation laws, and one of them I'll be talking about. It's called torque. I'm not even sure why torque, but I guess it's because it's vector product. But anyway, so it's a weird sum with some denominators, but you can check it's exactly commutes with the Hamiltonian. And of course, this is well known. So this model was studied a lot. And now this model is kind of, I would say, standard model of chaos in the sense that it's similar to the gas of this room. So what happens when we have a gas? So suppose we have zero interaction. Of course, it's integral. We turn on small interaction. Well, we write kinetic equations. Of course, kinetic equations are complicated, but we do some perturbation theory. And then we know if I'm sufficiently close to equilibrium, I can often use relaxation time approximation. And essentially, it predicts that I have exponential decay of my observables in time, and this rate is proportional to delta squared. Delta is strength of perturbation, right? And this is just time-dependent perturbation theory. So I have approximately exponential relaxation. So this is the expectation, and this works beautifully for this model. So, and here I'm talking about thermalization, right? Relaxation. There are no like Lyapunov exponents and so on. So this is example of what happens with this observable, and we checked what other observables are similar. There are some subtleties, but let me not go to it. This collapse works very well. So what's shown is relaxation of this correlation function of tau of t, tau of 0. So if I'm integrable, it doesn't decay. It's a conserved quantity. But if I'm not, it decays, right? And then what you see, different perturbation strengths. And the larger the perturbation, the faster it decays. But now, if we rescale time with delta squared, we get perfect collapse. And now if I look into the spectral function, I get nearly perfect Lorentzian, except for like high frequencies, you start to see some tiny deviations, which I don't know, maybe could be finite size effect, we are not sure. But anyway, it's a perfect Lorentzian, and again, it's shown in log scale, so it looks a bit unusual, but this is Lorentzian function, so everything works. And then, according to what I said, we can ask, where's the system most unstable? So let's imagine I fix my cutoff mu. So my mu is a waiting time. It's like basically how long I run experiment. And then I compute fidelity susceptibility. And it's a very simple integral. I said it's integral of spectral function, essentially up to 1 over mu. So it's a very simple integral, and I get an answer. And let me just think what this answer really says. It just says that if my gamma is really small, and small means smaller than mu, again, mu is inverse waiting time, its frequency, fidelity susceptibility is very small, which makes sense. I'm integrable, right? If my relaxation rate is so long, it's like time of the universe, and I wait for 1 hour, I have no idea the system is ergodic, right? And say it's not chaotic, right? Because in any experiment, it will not be chaotic. But then there is another interesting observation. Then if my gamma or mu, let me say gamma, gamma is very big, fidelity susceptibility is again small. It's 1 over gamma mu. So I see the system as, again, it's chaotic, but not very strongly chaotic. And the maximum of the chaos occurs exactly when gamma is the order of mu. So when the relaxation time, when the system is barely thermalizing, it just wants to thermalize. So if I wait this time, and this maximum is 1 over mu squared. Remember, mu is 1 over t. It's t squared. It's the absolute maximum which you can have. So the system becomes maximally chaotic according to these measures. Now, what about Lyapunov exponents? So actually, finding Lyapunov exponents is extremely challenging numerically, especially when nonlinearity is small. So we just thought about slightly different measure, which kind of becomes Lyapunov exponent, but which is much easier to measure. So we call it separation time. So you start from 2 nearby trajectories. You evolve in time until the distance between trajectories becomes some finite number. So here, d0 is basically numerical precision, a bit high. It's like 10 to the minus 12, something you can handle. And dt is 10 to the minus 4. It's still small, but it's like 8 magnitudes, 8 orders of magnitude bigger, right? And then you find this ratio. It's time to take to this divergence divided by log of this ratio of the distance. And you can see that if distance grows exponentially, it's exactly inverse Lyapunov exponent. But here we call it separation time because, as I'll show, when weak integrability, you don't really have exponential dependence until you wait like for very long times and so on. So, and then we study this separation time as a function of initial conditions. It's exactly about distribution. And this is the plot. So it's probability distribution. So here we have separation time, which is rescaled, but again, different nonlinearities. And then you basically see that most trajectories have separation time somewhere here, but there are some which are a little bit faster, there are some which are a little bit slower. Overall, it's a narrow distribution, and I want to emphasize it scales as time scales as 1 over delta power 2/3. Well, 0.65 is best numerical fit. It's probably 2/3. Actually, it's definitely 2/3 because there is actually a very nice analytical explanation by Boris Fine coming to 2012 on another model. It's really beautiful. He proved that this is 2/3, and this 2/3 was observed in another model. So we actually see something interesting, that Lyapunov time, which we define as average of separation time, again, when you have broad distribution, 1 over average lambda is, and average of 1 over lambda are not the same. So we look into physical, as we believe, object, average of time, not average of inverse Lyapunov exponent. So this we call Lyapunov time. And this scales as 1 over delta power 3/3, and it's much, much faster than relaxation time. So we see that in this scenario, which is termed as confined chaos, and this term was coined before us. Actually, this was sort of realized first in '96. And I said it's really common scenario you see for the gas in this room. Lyapunov times are like instantaneous. Well, instantaneous on this time scale. So now if I kind of want to summarize this into plots, I will say that if you think about this model, we usually have first dephasing time, integrable time. So this time doesn't exist for exact conservation laws because they just conserved. But if you take any other observable which has overlaps with conservation laws, even an integrable limit, it will take some time to settle through DGGE. So that's what we call tau phi. But it's time which doesn't depend on perturbation. Then after that, you will get Lyapunov time when you basically get dephasing, your TOC will decay and so on. And then we will get a melting time, and that's what we call when basically these conserved operators start to decay, really. And then thermalization time is when they reach equilibrium. And in this case, we see melting time and thermalization time, they're the same. They're separated by number. So both are like 1 over delta squared. Again, it's completely consistent with this exponential scaling. So maybe one note I want to make, which is important, that at the onset of thermalization, diffusion plays no role. Because if you were careful, you'll ask, how is it possible I decay exponentially? If I have perturbation like in this room, it will decay diffusively, which is power law. Well, the reason is that when we just introduce nonlinearity at fixed system size, it could be large but fixed, then you start from the limit when your relaxation time is, or rate is much shorter than tauless time. Because usually this diffusion coefficient diverges as delta goes to 0. Could be constant. So, but anyway, it's some finite time which is L-dependent, so it becomes longer and longer. Well, this frequency becomes smaller and smaller as L increases, but it's finite. But once you just start decay, your relaxation rate is small. And pictorially, just imagine I have integrable system, which is a soliton. And soliton moves back and forth, back and forth. You turn on tiny perturbation, this soliton will decay after many, many round trips. So in this sense, it will not diffuse. On the other hand, another order of limits, so if you have like ocean, right, the soliton will decay before it reaches the boundary. So it's a very subtle point, but so at some point, when gamma becomes of the order of this tauless time, we will have a crossover from this exponential relaxation to hydrodynamics. And I think it's very interesting to study. Yeah, and Lyapunov time, as I said, it's parametrically faster. So and now that's a physical picture of confined chaos, and that's most common chaos which we see. So what happens, and that's what actually was studied by Boris Fine carefully, then Lyapunov instabilities are along the tori. So essentially, the integrable system lives on tori, and then first trajectories become unstable. So if you have 2 moons, then with nearby initial conditions, then after some time, I think it's like 5 million years or something, the moons will stay on the same orbit, but you cannot predict angular distance between them. Even though moon is a bit special, it's super integrable, but I'll come back to that. But anyway, this is standard scenario. So, and this is some follow-up thoughts. So the physical picture, dephasing or relaxation of angle variables is much faster than relaxations of actions. And this is actually what we always use when we teach kinetic equations. We just say, oh, forget about phases, forget about this. Let's think only about occupation numbers. So it's intrinsic assumption in all this kinetic theory. So in a way, we know it for a long time. So, but then when we think about long-time observable chaos, and I'm coming back to butterfly, I was inspired by yesterday's talk, this chaos is described by kinetic equations. So it's only about actions when we talk about atmospheric instability. It has nothing to do with Lyapunov exponents. Or at least Lyapunov exponents are parametrically faster. So there is no difference in quantum and classical. We have same kinetic equations. Of course, there are some differences in collision integrals and so on, but once we write hydrodynamics, it's the same. So in this sense, like quantum chaos, classical chaos, Well, in atmosphere, is it quantum or classical? I don't know. Collisions between atoms are quantum, right? And there are no eigenstates, obviously, because times to reach them are like infinite. So in quantum systems, moreover, we see why Lyapunov exponents cannot be defined. By uncertainty principle, you cannot start from two very close initial conditions. And because tori are compact, phase variables are compact, there is no room to exponentially separate. And that's, I think, explanation why we cannot see Lyapunov exponents. So, and also, if you start thinking about experiments, even if gas is classical, defining chaos Lyapunov exponents is really unphysical. We need Maxwell demon. So if you are classical, you think about gas of this room, just think how you really set up experiment to observe Lyapunov exponents. You need a copy of the gas with same initial conditions. You will not be able to do it. You need to lower entropy at finite energy to like really crazily small numbers. Otherwise, you won't see exponents. Yeah, and this is, I added, it's butterfly effect, so it's real, but at least we believe. If butterfly will flap their wing, and a year, if we had a copy of this Earth, we'll get a tornado in Kansas in totally different place and time. So it does exist, but unrelated to OTOC. It's unrelated to operator spreading. It exists in quantum and classical systems, and it has to do with long-time instabilities. And then, yeah, I just mentioned quantum systems. I'm coming back to a work which we did with Marcos, and Dries was involved, and of course it was, as always, done by a student. So this is now quantum XXZ chain. So that time we didn't know about actions or angles, but we checked what happens with this XXZ chain with fidelity susceptibility. And here I just want to say in quantum system, I don't need to introduce frequency cutoff because it does exist naturally. It's a Heisenberg scale. So in quantum finite quantum systems, I can take infinite time limit. And there what we see is that what's shown here are different system sizes. Larger system size, of course, means longer Heisenberg time. And then I see that if I increase system size, I go from whatever, purple to red. I see that my fidelity susceptibility gets bigger and bigger, the maximum, and the scaling is 1 over Heisenberg frequency squared. It's exactly a maximal chaos 1 over mu squared. It cannot scale faster. It saturates the upper bound. And then what we also observed that you just see that this point where I have maximal chaos, basically when I have ergodicity, it scales very quickly with the system size. And this is kind of, it's consistent. It's not exact, but it's consistent with this Fermi-Golden rule ratio. Because if I say that gamma, which is proportional to, it should be delta prime squared, integrability breaking perturbation here, and I equate it to mu, which is Heisenberg scale, I will get square root. And numerics gives you roughly 0.4 exponent. So there is small difference, whether it's finite size effect or whether there are deviations from Fermi-Golden rule rate, we cannot say, because at this small integrability breaking perturbations, really hard to study systems. But anyway, I would say it's consistent. So it's likely confined chaos. So if you could study actions, angles, so operators, sort of like B dagger or B, if you think about particle numbers. So these operators which are orthogonal to, say, particle numbers. We would predict those relax faster. And actually, there was recently in Dresden colloquium by Kurt. I'm not going to pronounce his last name. And they showed this evidence that when they study these special variables, they relax much faster than actions. Okay. So, well, I'm going in the wrong direction. So how much time do I have? Okay. So we are done with first scenario, but the others will be a little bit faster because I kind of emphasized. Yeah, sorry, I pressed the wrong button. Yes.
So just there is no size dependence for the system?
Yeah, for classical systems, no, because we basically take thermodynamic limit. It's very easy classically, nothing depends on size. But for quantum systems, for quantum system, I showed only one. Yes, we show different sizes, but size only enters here through Heisenberg scale. because we study regimes where sort of diffusion and so on doesn't play a role. So this is precisely, sorry, I didn't put the label. So these lines are different system sizes. So the largest is 24, the smallest I think is 18. So it's 10, 20, 22, 24, yes.
How am I supposed to make the image?
So basically think about this. In quantum systems, so in classical systems, there is no Heisenberg scale. I have to introduce some time cutoff. It's equating time. In quantum system, there is a natural scale, which is Heisenberg scale. So it means I can still, there are papers we studied. So you can work with large system size and change scale as long as it time scale, as long as or frequency scale remains larger than Heisenberg, it's the same as in classical systems. But in quantum systems, once you reach Heisenberg scale, everything stops. Well, then of course you start getting some fluctuations and so on. By stops, I mean you get a different business, and there were actually very nice papers by John Chalker. You probably know about this, who studied this regime. So, but this simple story ends because there we need to start thinking about individual eigenstates because our time scales are so long. Then we have to. Yes, though you have to be again careful with this diffusion. It's not true thermodynamic limit. It's a limit where times are longer than Thouless times, but much shorter than Heisenberg times. But as I say, in this room, Thouless time is finite. Yeah. So even though this room is from Heisenberg point of view, it's just infinite, right? Once we go in the limit when even Thouless time is infinite, we have to be continued because we need to study space-time correlations.
Yeah, you get from Fermi golden rule, you get the mean free path, let's say, and then
Yes.
the Thouless time comes when you say, now my system is much, much larger than the mean free path, and then I have to scale with L square.
Yes,
right?
yes, yes.
So,
yes.
so you're saying
You
that in the classical case, you get essentially not system size dependence because you're looking at the.
Well, in my case, if
at
you want,
the
mean free path is actually much longer than system size because I just barely broke integrability.
Okay.
But the system thermalizes because you see particle moves many, many times, then it has a collision, then it thermalizes. But diffusion clearly doesn't play a role.
Okay.
So, but your limit, in your limit, I would say you have to study, well, as we expect, not just two-time correlation functions, but space-time correlation functions. But this has to be, I'm actually waiting for good students or postdocs interested in this because there are subtle. You can say, oh, let me look into structure factor, but it doesn't work like this. We really have to do it carefully because structure factors, they don't distinguish between integrable, non-integrable dynamics. You have to be, because you can have, say, diffusion in both, right? That people studied it. So, but I'm pretty sure, like, again, looking in the pictures, from space structures, we can also recognize chaos. So it's very interesting how we generalize all these fidelities, sensitivities to your limit, which is more physical. Okay, so I'm done with this scenario. So yeah, you can stop me at any point, but I don't have that much more. So, and then to our surprise, we found like totally different chaos mechanism in a different model. We used this, motivation was that let's just show that dimensionality plays no role. So let's try to find a model which is zero-dimensional and basically want to say diffusion doesn't show, which is integrable. And we knew actually through series of works, and Peter Kleist was there like a driving force, that central spin models are good examples. So it's a model where I have one spin, central spin obviously, with say only XX and YY interactions. But these are disordered. So, and in spin 1/2, it was proven, actually before Peter, I believe, that, actually maybe by him. It could be that he proved it first. Anyway, this model is integrable. For spin 1, that's definitely him. Well, and some students involved, but he was supervising. This model is integrable, but integrals now involve three spin terms and so on. For spin 3/2, they did exercise. They found some integrals which contain 4 spins, and then they didn't find all the integrals, but they still conjecture it's integrable. So by generalization, of course, you assume it's always integrable. So we thought, let's just look into this model, which is classical. Again, we won't compare classical to classical. And we do the same thing. We perturb it with small disorder on all spins, including central spin. And you just see this model is very simple. It's like central spin in collective magnetic field, but the point is only perpendicular. Again, I won't go into some details, but there is some already at integrable level, this model is extremely crazy. So if you look into these equations of motion, I mean, of course, you cannot really see much. These are like n equations of motion. Central spin moves in this collective magnetic field, and each individual spin moves in a field which is given by the central spin, right? So, and then it turns out, and this is really easy to check, but I don't want to do it in a talk, but if you just sit for 15 minutes, you'll see how it works, that if we work at zero energy, which means that this B is orthogonal to S naught. It should be S naught perp, but basically it doesn't matter. So B perp is orthogonal to S naught perp. It means that zero energy. Then directions of B perp and S naught perp don't change. I mean, if you can do calculations very quickly, you can kind of see it, because if B perp and S naught perp are orthogonal, you just see that the component S naught perp parallel to B perp doesn't change in time, and then by induction you conclude the same thing. So, and then this model is trivially integrable in this limit. So what happens basically, B perp and S perp, they have fixed directions. There are also some Z components, but it doesn't enter equations of motion. So if you want, they precess around fixed axis, but field is time dependent. So direction doesn't change, but field is time dependent. So it's still very complicated dynamics. And then I'm not showing this, but if you take any other energy, the model is chaotic. You get Lyapunov exponents, everything. So basically this generalization I made to infinite spin, it just doesn't work. Model is integrable spin 1/2, spin 1, spin 3/2, and by induction to probably in any finite spin, but integrals become less and less localized in space. And when you take classical limit, it's integrable only at energy shell. Moreover, the model is not just integrable, it's super integrable. Because now, if you believe my picture, you just see there are two L-1 integrals of motion. Why two L-1? There are perp directions of each spin. They oscillate, because if S naught is fixed, all Sj oscillate around the same plane. So these angles, precession angles around which they, basic axis or projections, let me put it, projections of all spins into perpendicular state, they're all conserved by direction. But also what happens is that they all synchronize, they move together. Because if S naught oscillates with one frequency and B oscillates, and then each spin oscillates with the same frequency, but then B oscillates with the same frequency and S naught also oscillates with the frequency, it's consistent. So anyway, so they all oscillate together. It's not harmonic motion, but it's the same period. And then you just see all angle differences, each angle, precessing angle now, it's time dependent, but these differences are also conserved in time. And I have L-1 differences. So I have not L, but two L-1 integrals of motion. And actually, the super integrability is well known. Again, for me, it was the first time, like David Long pointed to it. But it's well studied in literature, and it's known that the more integrals of motion you have, the smaller dimensional have the tori. So in this case, it's maximally super integrable on all your tori are one-dimensional. And actually, that's what happens for Kepler problem. You have one-dimensional orbits precisely because you have 5 integrals of motion. Lx, Ly, Lz, right? Energy, and this, how it's called, the special vector. Yeah, I actually have to teach it, but I always forget the name. Anyway, it's the 5th one. Okay, so now let's break integrability, and let's see what happens with correlation functions. And you might see that the pictures look exactly the same. So we take a conserved operator, it's one of the angles of the central spin, which I said is conserved, and see how it depends on time. It's the same Lorentzian decay. I have the same collapse with one subtlety. It's not delta squared, it's not delta squared, it's delta. So my time scale is non-perturbative. It's not given by Fermi-Golden rule rate. And actually, there is a heuristic explanation for this, and then we have more detailed explanation there as well. You can say, well, it's the same Fermi-Golden rule rate. But the fact that model is super integrable actually means that all operators, including integrability breaking, they have finite overlaps with some conserved property integrals, because there are too many of them. But then if you write this Fermi-Golden rule argument, you know, gamma is proportional to delta squared times spectral function of gamma. But this itself is 1 over gamma. From here, you just get gamma is absolute value of delta. And now if you try to compute separation times, you actually see that there is a very broad distribution. So what's shown, this is again, this melting time and thermalization time defined as before. It's basically when I decay to here and here. But then there are also separation times which are broadly distributed. And what's shown is here percentile perturbation strength. So this is basically a separation time between first 5% of trajectories. So it's fast. And then as you go higher and higher, then it's of course slower and slower. And you immediately see there is a very broad distribution. So there is no like a single Lyapunov exponent if you want. But they're all kind of in between. So now let's try to interpret what's going on. So the microscopic mechanism is very different from kinetic theory. So what happens is that I have this one-dimensional orbits instead of tori. And these orbits become really unstable because there are too many integrals of motion. So what happens is that once I break integrability, they start drifting. And the reason they start drift comes from time-dependent perturbation theory. Normally, we all teach or learn at school that if you do time-dependent perturbation theory or any perturbation theory for conserved operator, linear order vanishes because your operator and density matrix commute. It's a technical thing. But here they do not, because my density operator can be determined by totally different integrals of motion. Right? Say I define my states as functions of LZ, and I look into how Lx changes. They don't commute Lx and my density matrix. And because of that, like technical detail, have a linear drift, not quadratic drift. And in this case, as I said, this integral of motion is my angle of S naught. And then if I look, let's just look into yellow line. There are other lines, I just don't have time to talk about this. But yellow line is this angle, and you see it drifts linearly, and then something funny happens. It just jumps, it's a log scale. It jumps by like 5 orders of magnitude, and then it again drifts. So clearly there are some regions which we call chaotic pockets or beta manifolds, or if you want membranes. And these are regions of phase space where my integral period diverges. And then, of course, you know intuitively, any perturbation will distort dynamics, right? Because I'm barely moving, so if I introduce small magnetic field, my precession is faster than my motion. And when I hit this chaotic pocket, everything is destroyed. By everything, I mean both actions and angles. So the pictorial picture is like this. I have 2 trajectories which are close to each other. I bump into this chaotic pocket. Everything is destroyed, right? And then we call it deconfined chaos because there is no confinement. And again, this is the picture, 3 time scales, and as I said, Lyapunov time is in between. And here, I don't want here to make a strong statement, but maybe it's a speculation. There are lots of parallels with SYK model. So right now, I'm willing to bet like really expensive cognac against like, say, simple IPA. That SYK model is this example of deconfined chaos. So superintegrability implies high degeneracy of integrable orbits, in quantum language, high degeneracy of states. That's exactly what's happening in a SYK model. Single non-perturbative timescale for dephasing is 1 over absolute value of delta. And SYK, if we think about temperatures, integrability, breaking perturbation, and I can explain why, but it would be different talk, then I get 1 over T. Fermi liquid is T squared, right? J over T squared. And the third thing, there is no dependence of thermalization time on fast scale. Because if I have 1 over delta, there is no room for J, right? It's like if I have 1 over T, there is no room for J. So, and again, J here in our case, it determines like how quickly you move into orbits. But what's important is drift of orbits. So this is the mechanism. So, and there, deconfined chaos, we see it's rather a typical mechanism of chaos. So it's important not to make general conclusions. So, and this is my upset butterfly who just thinks because chaos in atmosphere is not given by SYK model. If it would be SYK, then butterfly would be happy because it's the same time scale, and then you can say whatever. It's OTOC or correlation functions or whatever. So if I don't know, if I have 5 more minutes, I don't have clock, so I don't know how long it takes.
Yeah, we are over time, but I don't know.
Okay, 2 more slides, but I can stop here. So the last story is a critical chaos, and this happens in disordered systems, Floki systems, few body systems. And I'm coming back to the example. It's a slightly different example, but anyway. So classical two-spin model, which is chaotic. And then if you now go back to spectral function, you will see that so for integrable trajectory, it decays to 0, which again means that my fidelity is finite. And if I have chaotic trajectory, this is now coming back to eigenstates, I have divergent spectral functions, but here you see it doesn't saturate. It's not Lorentzian. It just keeps going. And then if I look into different integrability breaking perturbation, then I also have like basically look in this line. So the spectral function's a power law, but it's a different power, 0.6. It's some in between. So this is not universal power. So this means I have power law relaxation in time, which lasts as far as we can say forever. And classically, there is no Heisenberg scale. There is no other scale when something happens. And then my spectral function decays as power law. And my fidelity subtability is 1 over mu 1 plus alpha. And as I said, when this alpha becomes 1, so it's 1 over omega, this corresponds to slow relaxation in time. It's a maximal fidelity subtability. So we can get maximum chaos if you want a subdiffusion approaches localization. So yeah, because I'm over time, let me just say briefly, what I wanted to say, it's actually 2 extremely talented students at BU who actually worked with David Campbell. I didn't show his picture because it's completely their proof. They actually proved that if you have correlation functions which decay slower than 1 over t, then it corresponds to weak mixing in classical systems and stronger than 1 over t, which basically means in our language ergodicity, right, or ETH. This is a strong mixing. So things connected together. So yeah, this is, I think, the really last meaningful slide. So the same happens in Anderson model. At criticality, we have power law with power, which you better ask Lev if you have questions related to fractal dimensions. This 0.52. So it works beautifully. This is at the transition. What's non-trivial that we see that there is a finite range of disorder where we still see the same behavior. So it looks like there is a non-trivial Anderson insulator in the finite range of disorder. And then the final thing is that if you take disordered fermions, and here we take classical limit or classical, if you want, fermionic Gross-Pitaevsky equations or self-consistent Hartree fork, doesn't matter. So we do it in 1YV, actually. I mean, Lukasz Iwanek and Adam Saina in Wrocław. Sorry about that, getting wrong direction. So you see again perfect 1 over omega scaling, both in 1D and 2D. There are slight differences that tau less time, basically the scale when 1 over omega should stop. It depends exponentially on disorder in 1D, and it depends as square root of disorder roughly in 2D. Anyway, so I'll guess because I'm over time, let me just give sort of a summary. So coming back to general picture, so if we think about loosely axis, 1 is time, could be Heisenberg scale, could be just waiting time, and was an integrability breaking perturbation, then of course we always, if our integrability breaking is small and I wait finite time, I think the system is integrable. It's more or less obvious. If I either increase time or I increase integrability breaking perturbation, I go to a region which is maximally chaotic according to at least susceptibility, but also I would say common sense. And there we can have like 3 different scenarios as I described. And then eventually we might again, because there are some exceptions like KM, we might go into ergodic regime where ETH works and so on. There is never a direct transition from integrable to ergodic. And here I just want to emphasize this point. Maximal chaos should be distinguished from maximal mixing or maximal relaxation. And I like to show this picture. Again, many people say SYK is maximally chaotic. I will say it's maximally ergodic, maximally mixing, but minimally chaotic. And the reason is very simple. Think about, again, outside. You have a turbulent gas. You have small interactions, basically small Lyapunov exponents and so on. And then you have a metallic spring. Of course, you will say it's not chaotic, but it consists of electrons, which relax in like picoseconds, instantaneously. So it's not chaotic, not because of large, whatever, Lyapunov exponents or fast relaxation times, but because of fast relaxations. Okay, so systems which relax quickly, they're much more adiabatic, they're much less chaotic. And this is finally my conclusions. So I told you that we can think about chaos. Quantum classical doesn't matter through complexity of this adiabatic transformations or just spectral functions in a simple language. So then the spectral functions or adiabatic gauge potential or fidelity, if you want, they bear information both about irregularity and instability of time average distributions. There are at least 3 regimes of reemergence of chaos: critical, confined, deconfined, and maybe there are more, but so far everything I know fits together. So Lyapunov exponents, they're really irrelevant, I would say even misleading for observing chaos in many particle systems, quantum or classical, with few exceptions like SYK, but these are really special cases. And then I would say the other interesting thing is that ETH, ergodicity, RMT, strong mixing, all these concepts, they actually can be understood through fast decay of correlations. And weak mixing or critical chaos or maybe fractal phases, at least it looks conceptually very simple, they can be understood through really slow decay of correlations. And they correspond to, in a way, strong chaos, strong instability. Okay, sorry for being over time, and thank you. But there is no clock, so I had no idea what I'm doing.
Okay, so it's our fault.
Then...
It's our fault. Yes. More questions? Okay, lunch is pressing. No, we have 1 question. Fantastic.
Okay, first of all, thank you for your talk. It was wonderful. I would like to know more about the fidelity susceptibility. And sorry if my question is too basic. We can use this fidelity susceptibility to follow a specific eigenstate under the variation of my Hamiltonian parameters, but you have like the coefficient is very similar to the standard coefficient of perturbation theory. You have a matrix element divided by the difference of energies. So what happens if I want to follow the same eigenstate to see how...
Follow as a function of what parameter?
About the perturbation parameter.
Yeah. Well, of course, there's a question how you do it, because numerically it could be very challenging. But if you want the same operator, like a adiabatic gauge potential, which norm gives you about fidelity susceptibility, it's also a Hamiltonian, which describes you how eigenstates evolve. So if you have exact adiabatic gauge potential, then you know both, right? If you apply it, so if you want to think about this, adiabatic gauge potential is a Hamiltonian which moves you between eigenstates as you change Hamiltonian, right? So it's the same object. But in chaotic, ergodic, whatever systems, it's super difficult to compute. And then you can use regularized adiabatic gauge potential as this mu. That's finite. But this moves you between energy shells.
Okay.
So it doesn't distinguish individual eigenstates within shell mu. But again, in no experiment we distinguish eigenstates. So in my opinion, that's as good.
And I was also wondering if we can use this fidelity susceptibility to somehow measure the or to detect the breaking of classical camptorize in the quantum version. I don't know.
Yeah. Well, that's what I showed. You can distinguish both integrable trajectory or regular trajectories, how they called, and chaotic trajectories. And analog should be the same with eigenstates. So you can distinguish regular eigenstates if you have mixed phase space region from chaotic eigenstates.
But like you can set the specific value of the perturbation parameter at which a given eigenstate.
You take, well, wait. So it's one perturbation parameter, it's how much you break integrability. This is your parameter, and then KM systems could be finite, or like Anderson, Anderson insulator, it's finite, it's disorder 16.5. Maybe you can think about this perturbation as 1 over disorder. So it's a finite number, right? But then you ask sensitivity to infinitesimal perturbation. That's why it's susceptibility, right? Susceptibility is always defined what happens if you infinitesimally deform Hamiltonian on top of whatever you have, how the states would change, right? So susceptibility is linear response.
Okay.
But you can study it as a function of integrability breaking perturbation, which is finite.
Okay, thank you.
Jared?
Yeah, can you?
So all these examples you gave basically had like one type of perturbation. If I imagine having a second, but non-commuting with the first direction, maybe I can have a two-dimensional, like, you know, I can spin a two-dimensional manifold. Do you think we can have different types of chaos coming in different directions, maybe?
Yes. Well, I'm not sure about types. I had to study this a bit. Like, well, actually, no, I'm lying. We know definitely in the central spin model what you are saying is true, because if you study this system as a function of energy difference, right? Just said this model is only integrable at energy 0. This is middle of the spectrum. It's not zero energy, doesn't mean ground state. It's middle of the spectrum. Actually, if we use energy difference as another perturbation, you actually have this critical chaos. You have KM, you have, it's really crazy. So definitely you have dependence on perturbation, that's true. But even in normal systems, we know that there are actually perturbations at the integrable point. There are perturbations, there is first, of course, let me say observables, right, or lambdas, parameters, which are kind of parallel to integrability and orthogonal. If you break integrability a lot, it doesn't matter. They kind of all local observables sort of are the same. But if you're close to integrable point, you have super strong anisotropy in fidelity susceptibility. Now, how they decay? Of course, they decay differently, because if you take observable, which is kind of orthogonal to your breaks in integrability, then it will relax at finite time, even at integrable point, because it doesn't have any overlaps, any Drude weight, so it will just relax to 0. But if you take a parallel observable, it will not relax. Now, if you break integrability, you have strongly anisotropic relaxation. So you're absolutely correct that close to integrability, we have to deal with geometric tensor, not, and then, yeah, there is a very interesting geometry. You have singular geometry associated with this geometric tensor. It's really beginning of an iceberg, I think. Geometry is super interesting. Geometry of chaos is super interesting.
Like also like aside the geometry, I can, I guess, define some sort of Berry curvature.
Yeah, this we didn't study, but it's also very interesting. I would say think about this as criticality, right? Usually we say one parameter, but it's not the case, right? Because you can have relevant perturbations, irrelevant perturbations, marginal perturbation. It's the same story here. So it's actually there is a lot, there are many parallels between emergent of chaos and critical phenomena.
Okay. Okay, so let's thank Anatoly again.